Hello and welcome to this mini online lecture on PID control. My name is Dr. Anthony Chen from the Department of Electrical and Electronic Engineering at the University of Manchester. Today, we're going to explore how control systems are used in engineering applications, focusing on PID control design and its application with example on altitude control for aircraft. The PID control is widely applied in engineering, for example, for aircraft to maintain stability and achieve a specific flight objectives. So by the end of this lecture, you will have a solid understanding of how we design a PID controller to tackle common challenges in engineering. So let's take a quick look at the history of the PID control, which has evolved over the past 100 years. So the earliest application of feedback control was in 1911 by Elmer Sperry. So we used a proportional control method to stabilize some ship steering system. So this basically laid the foundation for the feedback control principles. Then in the 1922, it's Nicholas Milevsky, who was a Russian-American scientist. He formally developed the concept of PID control. That was the birth of PID, which means three components: proportional, integral, and derivative, which was a very effective method at correcting errors. Then in 1942, we have Ziegler and Nichols proposed this tuning method, which is famously used. It's widely used in industry settings, still using today. And then in the 1970s, for Astrom developed its adaptive, or we call it auto tuning method, for tuning the PID gains, that basically enhancing the robustness in real world application. Then, of course, the rise of digital technology in the 1980s made it possible to implement PID controller in software. That's with the booming of electronics and avionics in aerospace. And then until recently, the machine learning and AI was booming after the 2010s. And there are some intelligent control method that we can make the PID controller smart, which means they can self-tuning as well based on the different operating conditions, such as my work recently. So what is a PID control exactly? We can start by writing down the mathematical form of the control law. So U of t is the control input, such as the propeller speed of the aircraft, and the E is the error term. We now can see there are three components. The first component is the P component, proportional, and the second term is the Ki component, integral, and third component is Kd, which is the derivative. So in the industrial setting, there's a more standard form. You can also write its equivalent formulation like this. So instead of writing Ki and Kd, we can use Ti and Tg, which are the time constants. And this helps us to have an intuitive understanding of the parameter and how to tune it. To help us understand the PID control, we can graph it out in a block diagram, something like this. So the first term is the proportional control, is the P component, which adjusts the systems based on the size of the present error. For example, for altitude control, if the aircraft is below the desired altitude, the proportional control can increase the input, the control inputs like the propeller speed to push the aircraft back up. But the P component itself is not enough because there's going to be oscillations and some error, then like steady state error. Then we have the second term, the integral control, the I component, which solves the issue of steady state error because it accumulates the error over time to the integration and adjusts accordingly. So for example, if the aircraft has been slightly below the target in a steady state, the integral control will gradually increase the propeller until the steady state error is eliminated. So it's based on the past information. And similarly, for the third components, the D control, derivative components, it predicts the future trend of the error by looking at how quickly the error is changing, which is the derivative of the error itself. So if the aircraft is rapidly approaching the desired altitude, the derivative control applies a counteracting force to slow the approach, so preventing overshoots and creating a smooth response without oscillation. So let's move on to the controller design process, which will help us understand the PID controller better. So the case study we're considering now is an example of altitude controller for a quadcopter drone. As you can see, I draw the drone there. So imagine it sits on the ground now. So the aim is to lift it up on the air with the altitude around 50 meters. Say it moves like this. But if you apply the controller, there are going to be some error, Y and E, and that's the reference R. So basically the arrow, we can write it down as E equals R minus Y. So the control objective now is we want to minimize this error. Ideally, the E equals 0. So we can start by looking at the PID control term by term. So for the P control, P components, we can write it down as U equals KP times E. So the U is the control propeller speed, the control input. KP is the gain, and arrow, which is E. And then assume that the UAV, the drone, needs to hover using, say, the propeller speed is 100 RPM. So basically, if we set the control gain as 2, KP is 2, then the arrow is 50. So this basically means if the arrow is 50, basically means the drone is on the ground. So it's hovering on the ground. So we can increase the P gain. Say we increase it to 5, then we can calculate the arrow will be 20. So the arrow is reduced by increasing the gain. So we can just do it further, increase the gain to 10, then the arrow goes to 10. But we can go up to, like 100. The arrow becomes 1. So it looks good when you don't care about this arrow, but this arrow is not going away. This is something we call steady state error. And so that's why the P control itself doesn't have a solution to completely remove the error. That's why we need the other components like I and D. So when we combine the PID controls, we create a robust altitude control system, something like this. So remember the control law is PID, then we can connect and close the loop. So based on the arrow E, reference R, we have control input is the propeller speed, and the output in this case is the altitude of the flight of the aircraft. So the proportional component basically handles immediate altitude changes, based on the present error. So the integral components correct any lasting deviations based on the past error, and derivative components ensures smooth, stable adjustments based on the future error, future prediction. So together they form a PID controller that can maintain altitude with a minimum error. So in practice, how do we determine the values of the parameters of the PID gains? Say, this shows you how the PID 3 gains affect the performance individually. So we start by looking at when we have KP only, KP is 1 now, and we increase it, it reduces the error, but there's a steady state error at the end. So we bring in the integral term that removes the steady state error, but there's oscillations. And then we introduce the KD term, which helps us to smooth the response. So we can look at it again. So proportional term, integral term to remove steady state error, but there's oscillations. Then we use derivative component to smooth that. That's the overshoot we're reducing now. As we understand, the PID control is very powerful. However, in real life, there are always challenges. For example, the disturbances from the environment, some actuator limits or constraints, or the nonlinearity of the system. For example, for altitude control of the aircraft, there are unknown disturbances from the wind or turbulence. And also for actuator limits, we have throttle limits. There's physical limits on the propeller speed, and also we have the nonlinearity, which some nonlinear behavior like the drag force do not increase linearly with the speed. And all these problems, I mean, is the PID controller can deal with them, but not effectively. So that's where we need more advanced control methodologies like adaptive control, robust control, optimal control, and that's going to be covered in a later course. So let's summarize what we have learned today in this lecture, the key takeaways of the intended learning outcome. The first one is the PID control basics. We understand the three components. The P components consider the present error, I for the past errors, and D for the future errors. And also we investigate the PID controller in a practical problem like altitude control problem of an aircraft. And thirdly, we also aware of the practical considerations. There are some tuning process involved, and there are some real world challenges that cannot be handled easily by the PID control. So some add-on. So for tuning process, today we covered how we manually change the PID gains, but also, I mean, there are more advanced methods like the regular Nichols method, and also even recently the machine learning method for a smart PID. So here are some references of today's lecture, and there's also a further reading. If you want to know more about PID controller in general, I suggest you to read the book by Estrom, which is a very well-known book called Advanced PID Control. And make sure to check out the MATLAB Simulink software. So they have really good resource, and you can play around the PID games, see how it really works in practice. And if you have any questions, make sure you email me. Thank you and enjoy your studies.